Welcome to springlib.
In this problem, we have a connecting rod is supported by a knife edge, and we're told that for small oscillations, the angular acceleration of the connecting rod is governed by the equation. The angular acceleration equals -6 times the angular displacement. We can write the angular acceleration in terms of the angular displacement, which is the second time derivative or the first time derivative of the angular velocity. We can write this expression here, basically using the chain rule. The chain rule as the angular velocity times the derivative of the angular velocity with respect to the angular displacement. Now, there's various ways you can solve this problem. If you've taken differential equations, you can see that this is a differential equation, and you could just solve that differential equation. If you have it, then you can just use some calculus here to figure out what the answer is. So we have we're told that theta 0, so at t equals 0, we have is 20 degrees or 0.349 radians. So we can take this expression here and here, separate variables, and then integrate. So we get an integral from 0 to omega of omega bar d omega bar, and an integral from theta naught to theta of -6 theta bar d theta bar. Doing the integrals, we get 1/2 omega squared equals 3 times theta naught squared minus theta squared. We can solve for omega. And we can see clearly that omega max happens when theta equals 0. And we can plug that value in and we get 0.855 radians per second. Now, let's see here. We can then use the relationship that the angular velocity is the angular displacement, the time derivative of the angular displacement, again separating variables. We get the integral integrating, we get the integral from 0 to t dt bar equals the integral from theta naught to theta d theta over omega, but we know what omega is in terms of theta from here, so we plug that in. And then this integral here is simple. This integral here is a nightmare unless you have a computer, or just remember, look it up, how you integrate a square root of this kind of integral. And it turns out that that side is -1 over square root of 6 times cosine, the inverse cosine of theta over theta naught. We can, invert this equation to get theta in terms of t, and so theta equals minus theta naught cosine square root of 6t. One thing you can do is you could actually plug that back into here and see that it, in fact, satisfies this differential equation here. Now they ask for theta at t equals 2, so we can simply plug in t equals 2. We know theta naught, and that winds up being 0.0645 radians, or 3.69 degrees.